So these pockets of microgrids are connected across the distribution systems primarily, and it could be categorized further into rural sector, urban sector, semi-urban, depending upon the kind of generations that we may have. Rural microgrid can have a biomass, photovoltaics, could be wind power plant, could be part of the generation side, and and if you go to the urban side, then primarily we don't have space for wind plants and the biomass as such. So solar photovoltaics uh, will be the only available renewable energy sources, more or less. So, and then fuel cell can be also part of it. Green hydrogen storage. So the main principle of a microgrid operation would remain same in spite of we think of the rural or urban application, but the overall their intent to do this primary purpose of establishment of the microgrid, which is to cater to the requirement of the local energy demand and also exchange excess energy with the grid or absorb lack of energy which is required in the microgrid from the main grid, so that the load which is connected to the microgrid premises, they will be getting a reliable quality power supply. Thereby they also contribute towards what is in today's world, which is a kind of very important aspect, which is called as grid resiliency, right? So we're going to discuss all of them piece by piece, so that towards the end you get an idea about how a microgrid would look like, and then be really able to appreciate the 2 hour sitting session today. So if I have to explain you in a nutshell, microgrid is a localized group of electricity sources and loads that normally operates connected to and synchronous with the traditional centralized electric grid, as I rightly mentioned, and but can also disconnect to island mode and function autonomously as per physical and or economical conditions, right? So you see this, if I have to portray the display of a DC microgrid, so microgrids could be DC, a AC, or a hybrid combination. If the common bus wherein the generator and the storage and the loads are connected is of DC in nature, so then we call this as a DC microgrid. So let's have a DC rail which is running in common for all the microgrids. So each microgrid can have solar photovoltaics, wind, and then storage and the cluster of loads, and then they get connected across, so that microgrids can also talk to each other and exchange energy, so that they can have their own independent sustainable model, both technically and economically, bringing out multiple advantages for the end users. So microgrids are small electrical distribution systems that connect multiple customers to multiple distributed sources of generation and storage. So today's topic, we are highlighting more about the DC side of a system. Though we need primarily DC and AC both in the network. The importance of DC, it's quite obvious that the generation which is predominant in the whole renewable energy sector is the photovoltaics, and they generate electricity in the form of DC. So that is a major motive why we have to look into the DC system because the generation is DC. And then look at the load side. Most of the electronic gadgets data centers and electronic gadgets, they require DC supply. So loads are also of DC in nature. And the storage unit, which is very very essential, as we all are familiar about the generation profile of any renewable energy resources. For example, if you want to talk about the photovoltaic system, we have solar available during the daytime, and the night we don't have any energy coming from the solar photovoltaic panels. So in that regard, so the batteries are very essential, because you can store the excess of energy available from the photovoltaics during the daytime, and you can cater to the load requirement using the stored energy with the help of these battery storage systems. So the generation, load, and the storage units, they all inherently in DC in nature. So henceforth, forming a common DC bus to connect them will be much more efficient than to go to the DC system and then come back from AC to DC. The losses can be avoided. So henceforth, the DC microgrid is picking up also very aggressively across the world. So importance of DC, already some of you may ask this, and already we have a AC system, why do we need to go for a DC grid? So the other technical merits, apart from the inherent nature of a generation, storage, and the load, which are DC in nature, so these points will really give you extra confidence why we need to really think about the DC microgrid. So various conversion stages like AC to DC, DC to AC can be avoided by forming DC grid, and overall system efficiency can be improved, as I rightly mentioned. So the conversion losses can be eliminated, and then significantly the system efficiency will also boosted. No problem of a reactive power compensation, because the reactive power has no role to play in the DC system. Harmonics will be also not there because frequency is zero. Frequency control will, that problem will also be not there in the DC system. If you think about the AC system, the synchronization require the magnitude, phase angle, and the frequency need to be matched with the existing grid. So such cumbersome synchronizing principle is not at all required in the DC system, because it's just straightforward, and a relationship exists between active power and the voltage. So bringing down the complex four variable system to just two variable and straightforward relationship between the active power and the voltage, making it much simpler for a synchronization or interconnection, I would say, and the controlling as well. And apart from this, the other minor losses that we also see in a AC system, like eddy current loss and a hysteresis loss, a skin effect, absence of skin effect, all of them will be an extra, what do you say, benefit in the case of a DC microgrid. So, and apart from this, the reduced stress on conventional grid, congestion of transmission lines will be also reduced. We are not here propagating that DC system should be only system that should be existing in the whole world. AC is predominant. AC system is must and should. It's quite robust, time tested. Protection system is much simpler. AC has its own protocol of advantages, and we also have a DC system which has its own inherent merits. So what we are going to say is DC and AC should go hand in hand. Wherever you feel like DC system is a pick of a choice, then we should go for a DC system. Otherwise, by default, AC system is already lined up, empowering all of us in terms of giving energy to the critical to the existing load system. So DC operation voltage levels, HVDC, MVDC, LVDC. HVDC is again a time-tested research area, and it's many HVDC bipolar links have been laid out. Numerous merits, because two separate AC networks operating in different frequencies. If you want to combine together, in fact, people are talking about one world, one frequency, one grid, right? So if you want to make the whole system, whole world looks like one grid, so Vasudeva Kutumbakam kind of thing in the whole in the electrical language. So then in that case, because system they themselves are working in different frequencies, you need bipolar HVDC links to get interconnected for more economical and efficient operations, and also to improve the reliability of the network. And also HVDC is proved to be quite economical when you go for long distance transmissions. And also HVDC lines are helping in terms of improving the power transfer capability of the lines as well. So, and also there is a concept of MVDC, which also is helpful for improved power transfer capability between two different AC lines. And then LVDC is what we are talking about. Operating voltage levels are around 48 volt, 380 volt, and 600 volts. So they help to reduce the dependency on the main grid. Reliability to the customers can be improved and provide supply to the remote villages. And you can just recall the recent development that is happening in the transportation sector also, where people are speaking about aggressive implementation of EV charging stations. So most of the EV charging stations are also coming up with the rooftop PV panels. So henceforth, we can also think about expanding this to the DC microgrid concept can be expanded to the EV charging station as well, where the load is the EV chargers or the batteries, and the battery themselves can be bidirectional also. So storage and the load, and then local auxiliary supplies which may be required, and in the generation could be solar photovoltaics themselves. So that they themselves EV charging station could itself be a DC microgrid for us, and then. We can see such kind of plans in numerous numbers coming up in metropolitan cities to start with, and it makes expand to various other sectors also, including rural and semi-urban. So what are the topologies available for a DC microgrid? It's a single bus topology, quite straightforward. You have a DC bus, and then different generations like photovoltaics, wind may also get connected, and the battery and the supercapacitor. The combination is called as hybrid storage systems. They may also get connected with respective converters, and the fuel cell, which is also gaining a lot of popularity because of green hydrogen. Targets that we have in this country, and then the lighting loads and the heating equipments, the communication towers, data centers, all of them can be part of a DC bus integrated system. So right, and then so the operates at plus or minus 170 volts. Multi-bus topology. So the second topology is a multi-bus topology, where you can think of DC bus 1, which can represent one microgrid, and DC bus 2 could represent another microgrid, and there could be a common load which is served by both the microgrids. So you can also think of connecting two different village microgrids, and then exchanging power among themselves, so that we can have more reliability basically. Such kind of implementation is done by IIT Kanpur. Close to IIT Kanpur campus, there were two village hamlets, Bargadia Purva and Chabbanivada. So these two village hamlets, when IIT Kanpur took up this project, I think a decade back, so there was no much electricity available in these village hamlets. So, and then gradually the power system network was developed, including the transmission lines and the distribution lines with the support from local distribution companies, and the specific microgrid was established with each village hamlets having its own generation in terms of biogas, and then battery lithium ion based battery technologies were placed, and also solar photovoltaics were there, solar water pumps, and the solar street lights. So the whole village got converted into a local power hub, so to take care of the local energy demand. So, and they also got interconnected with the help of AC to DC and AC converters, and then power exchange was happening. So remember, what we have done was AC microgrid as such, but that concept can be extended to the DC microgrid if a suitable application is found, which require the DC setup in that regard. So dual bus separately fed DC microgrids simultaneously supply from multiple buses is possible, and hence total efficiency is improved, and the reliability, as I rightly mentioned, is one of the important advantage of this kind of topologies. And then the ring configurable topology, where a DC ring bus architecture is proposed. So I hope you are all very familiar about the DC, the advantage of a mesh network as compared to the radial network in the AC system. So radial network would have significant voltage drop, so that, and the reliability will be also quite poor as compared to the mesh network. The similar concept can be brought in to the DC ring system as well, where if there is a fault in one part of the network, the power can be transmitted to the other side, so that the reliability of the network can be improved. So various generations and loads and storage units are connected at different point of common couplings to the common DC ring system that is laid out here. So what are the key energy sources of a microgrid? Photovoltaics, wind, and fuel cell. Now let's see the recent figures. I think the data is a little old, May 2025. So the generation of from the renewables is around 226 gigawatt. Solar being the dominant one with 110 gigawatt, and wind power is also there, 52 gigawatt. So that brings us to the point of discussion, the wherein we need to discuss in detail about the photovoltaics, and then we'll take up the wind power plants as well. So you know the basic funda of how solar photovoltaic would work. So the sunlight's packets of photons, whatever energy is received, and then the electron jumps from the valence band to the conduction band, and then the electricity that you produce is being consumed by the local loads or can be fed to the grid as well. So this is a PV cell equivalent model representing a single diode equivalent circuit. So there is a constant current source, independent current source, and then the diode which is there, and then RP and RS indicates that the photovoltaic cell will have its own representation of a voltage source and as well as the current source, right? How do you represent the current source? So we represent the current source by adding a parallel resistor with the current source. And how do you represent the voltage source? By adding a kind of series resistor in the system. So if you plot the IV characteristics that I am going to show you in further slides, you get to know that the IV characteristics of a photovoltaic cell would give us an idea that at some point of time the current remains constant, and at some portion of the IV the operating points where the voltage remains constant. So inherently the PV cell can be modeled to be as a constant current and a constant voltage source also. So these are the design equations for ideal PV cell and the practical PV cell. So this is what is the characteristics curve I am speaking about. So you can see this portion of the curve which looks like a constant current source, and here even it looks like a constant voltage source, though it's not ideal. Henceforth, to include the non ideality, we are going to add this parallel resistance RP and a series resistance RS in the network, right? So and since the current characteristics looks like of that of a single diode, so the diode is also being connected so that we get to model the exact behavior of the practical PV cell through this equivalent circuit, so that that can be used for our further circuit analysis. So this is your IV characteristics, where current is plotted in the y-axis and the voltage is plotted in the x-axis. There are three operating points which is of importance for all of us. One is a short circuit current, and then there is open circuit voltage. Across this photovoltaic cell, if you short, and the current that you measure, that is called a short circuit current. And if you open the photovoltaic cell and there is no load getting connected there, and the voltage that you measure is called the open circuit voltage, right? And then at both these points, the short circuit current point and the open circuit voltage point, either the voltage is zero or the current is zero, and hence the power remains zero. So both of these points wherein the current and the voltage, they may have their highest values, but unfortunately the power remains same. So it is not an important uh, idea, or it's not a very good idea to operate at these points. So henceforth we need a point of operation wherein maybe the current is not maximum or the voltage is not maximum, but the product of both of them is maximum. So that's called as a maximum power point. So IMP is a point of current is on the y-axis, and then the VMP is the voltage that is measured at this operating point of maximum power transfer. So VMP into IMP gives the maximum power delivered from the photovoltaic panel to the load. What is this challenge of MPPT? I'll explain you here. Let's say you have a photovoltaic source, PV source, and there is a load. Load has its own characteristics curve, and IV characteristics of a photovoltaics is also very familiar to us. But unfortunately, the load operating point and the photovoltaic cell operating MPPT operating point may not be the same, because we cannot insist the load to carry a particular current unless and until you have the capability to do in certain areas where, let's say, you have a battery storage system and put together you can charge and extract the maximum power. That's a different story, but otherwise mostly load is not in our control, and photovoltaic cell characteristics curve is also not in our control. It depends upon the manufacturers. So, and also operating conditions like the irradiation, temperature, based on all these things, the IV characteristics curve would change. So henceforth, in real time, so we need a smart algorithm and a device which will help us to match the impedance of the photovoltaic source with the load, so that the maximum power can be delivered from the source, that is photovoltaic source, to the load, right? So such an intermediate stage of conversions is called as power interface, where we have a power electronics DC to DC converter, which is being guided by a MPPT algorithm, which receives the inputs from the photovoltaics, like voltage, current, and grid operate. The atmospheric conditions like temperature, irradiations, and the output of the converter is also being sensed and fed to this algorithm. And in real time, it would guide the MPPT algorithm would guide these converters to operate at a specific duty cycle by switching on and off these switches which is present in these converters, so that the converter and the load put together looks like a MPPT point as seen from the photovoltaic source. So this is the whole philosophy of the operation of MPPT. So inherently, we have a photovoltaic source as a panel. The type could be monocrystalline, polycrystalline, or thin film, and the power interfacing device where we have these type of converters. Either could be single stage operation or dual stage operation, isolated or a non-isolated topologies, buck boost, buck boost, and could be inverters also, half bridge, full bridge, or NPC, ANPC types. And then you have a controllers, MPPT controller. The controller primarily need to track the MPPT, and it may also have embedded functions of inverter control as well. And the load could be AC grid, battery storage system, or the resistive load. So to have more pictorial representation of whatever theory that I have discussed now, you can just look at this picture where a load is simply connected to the photovoltaic panel, right? So then you just mark this short circuit point where the resistance is 0, and the open circuit point where the voltage is so maximum and the resistance is infinity basically. So then this is your MPPT point, but the load resistance R naught, and 1 by R naught is the slope of this line. So, and wherever the load line meets this IV characteristics is the operating point. Clearly you can see here that the operating point is not an ideal operating point wherein we are getting maximum power delivered from the photovoltaic panel to the load. So this is not a desirable operating point as such, right? So, and also you can see that when we plot the power versus voltage of this photovoltaic panel, so it depends upon the irradiation primarily. So you can see that as irradiation changes, the MPPT point also significantly changes. That calls us for a smart algorithm which would guide the MPPT, which would decide and has the potential hardware interface to realize this MPPT point being achieved in spite of different operating load resistance, which is not in our control in the practical case. So power loss during maximum power tracking. You see, if I operate at this MPPT point, this is the power that I'm going to get. And if I operate as per the load line, so this is the power that I get. So this is the amount of power that gets lost. So then that's the background why we need a power electronic interface. So this power interface, as I rightly mentioned, senses the voltages and the control input is generated and given to this power interface. And this power interfaces could be isolated or non-isolated. So now let's discuss about connecting a boost converter to the photovoltaic panel, where boost converter is helping us to track the MPPT, right? So many of you maybe from power system background or powertronics background, I don't know, but I assume that I have to give you basic understanding about how this converter would work, and then we'll discuss about the operating points and how this boost converter can be helpful for us to track the MPPT. So you can see here there's a photovoltaic panel, right? So, and then this is connected to a boost converter. There's input inductor, there is a switch. The switch could be IGBT or MOSFET, which is capable of operating at high switching frequency. And then you have a diode, and then there is output capacitor. There could be an input capacitor also, which may not be mandatory for a boost converter minded, but this input capacitor may also require to eliminate some ripples which may be coming from the photovoltaic panel. So in the boost converter, this input capacitor is not mandatory, but in buck converter it is essential. So, and then there is a load resistance which is varying and is connected across this output capacitor, right? So we have this topology now in our control. So you know the operation of a boost converter, right? So the output voltage will be higher than the input voltage, and it depends upon the duty ratio. Practically, if in theoretically we say that when duty ratio is 1, or the switch is always on, then you should be getting the ideal. Theoretically, it's an infinite voltage across the load resistance, but practically, that logic doesn't work out because of the saturation of the inductors, and will not be able to operate the switch all the time at at this at a position where it is kept on, because in that sense it gets shorted and there is no point where the diode conducts and the capacitor would discharge and the output voltage will never be infinity. So that the theory in practical there will be difference that you can appreciate that. So in practical sense, 3 to 4 boosting factor is quite possible, right? So that means whatever is the voltage, let's say 100 volt is the input voltage and the output voltage could be 300. And please mind it, for the rooftop applications where we have limited rooftop space available, you can only place less number of panels, right? So each panel could be 320 watt, 32 volt, or in this range 36 volt. So if you want to operate at the grid feeding mode where 230 volt is our AC side voltage, so you need to have large space to connect them together, or the other option could be with limited number of panels. If you use a boost converter, then the output voltage will increase, which is essential for us to connect to the inverter, because you need at least significant amount of double the voltage required at the AC side, that is around 500 to 600 volt at the DC side, which is essential to boost to feed the power to the AC network. So the henceforth the boost converter makes sense there. So the equations. I'm not going to discuss about how we have come up this. We got these equations. I hope that you know these basic things. The output voltage and the input voltage relationship. Voltage V0 is the voltage measured across the load resistance, and VPV is the voltage measured output across the PV panel. So this relationship is V0 is equal to VPV by 1 minus D, where D represents the duty ratio, right? Turn on time by the total time, right? So, and the current equation is just the opposite. I0 is equal to IPV into 1 minus D. This is like a conventional transformer. If the voltage boosts up, step up transformer, right? Equivalent to step up transformer. If the voltage boosts up and the current will buck, so output current will be less than the input current. Henceforth, the power remains almost the same from the input to the output side, except the losses that may happen with the inductors and the switches here. So more or less, it is very highly efficient. And then with this voltage equation and the current equation, we get a relationship between R0 and RPV, right? So VPV by IPV is the RPV, V0 by I0 is V0, so V0 by I0 is R0. So the relationship between the resistance, the load resistance and the resistance as seen from the PV panel with respect to the duty ratio is RPV is equal to R0 into 1 minus D the whole square. Now there are two extreme operating points possible. When the duty is 0, that means switch is never turned on, and the duty is 1, where the switch is never turned off, right? Let's see these two operating points. The extreme operating points are the relationship between RPV and R naught in these two operating points. So when duty is equal to 1, so R naught into 0 will be 0. So RPV is 0. That means it looks like we are shorting this photovoltaic panel, and that gives us what is the operating point in the IV characteristics is a short circuit point, right? When you're shorting the PV panel, it's a short circuit current that flows. So one extreme operating point is the short circuit point. And then if duty is 0, then RPV is equal to R naught. That means the maximum resistance as seen, the minimum resistance that can be seen from the photovoltaic panel is 0, and the maximum resistance that can be seen from the photovoltaic panel is the load resistance itself. So this entire region is the operating point available for us when we use the boost converter as a pick of choice to extract maximum power from the photovoltaic panel to the load. So the biggest challenge over here is, if for any reason, if this load line lies above the MPPT point, let's say somewhere here, then no matter what you do, you will never be able to track the MPPT from the photovoltaic panel. So I hope this is clear. So in order to give better understanding, what I would like to do is to give a MATLAB demonstration right here, so that you appreciate the operation of a boost converter with the MPPT. Let me stop this and okay. Yes. Can you all see the MATLAB model?
Yes, sir.
Right. So I have a MATLAB model. You can see that there is a photovoltaic panel. So I've connected two parallel strings, 5 series connected modules. So you can choose here. There are different manufacturers models readily available, and I'm just choosing my own. So it's a user defined, and cells per module is 36. Each module has different cells connected in series and parallel, and then the open circuit voltage of this particular panel is 50 volt, and the short circuit current is 6 amps, and the voltage at which maximum power point is tracked is 40 voltage. Certainly it is less than the open circuit voltage, and the current at the maximum power point tracking is 5 amps, which is also less than the short circuit current. But the what is the maximum power delivered? 40 into 5, that is 200 watt. That also you can see here, maximum power delivered is 200 watts. If you want to plot the IV and PV characteristics and want to see how it looks like, this is how it looks like. Right, this is current versus voltage, and power versus the voltage. And if you also want to check how the IV and PV characteristics would change for different operating conditions, that also you can check. I'm just giving different irradiations, 1800 and 500. Now if you want to plot, you can see here, as the irradiation changes, the power output will also change, right? So but we'll discuss now with 1000 irradiation for the sake of simplicity. So yes, we have a array standard operating conditions of 1000 watt per meter square and the 25 degrees Celsius, which is the standard operating temperature in the radiation. 200 watts capacity panel. Such panels of two numbers are, five numbers are connected in series, and such 5 connected series panels are connected in parallel. So the total power output from the entire string of array is 10 into 5, that is 2 kilowatt. It's a 2 kilowatt maximum power array that is available for us to meet out the load demand. So this is your photovoltaic panel, and I'm giving this irradiation and temperature also. You can program this to change in real time, but for the sake of simplicity, as I rightly mentioned, I'm just fixing these numbers, 1025 degrees Celsius. And then this is the load resistance. So let's keep this around 80 ohms. I have a load resistance of 80 ohms. So it's a MATLAB model. So power GUI block is required. You can either go for continuous or discrete. For hardware implementation, you need discrete, because this model may have to talk to the controller which is sitting outside. So that works in the digital platform, and discretization is must and should. So we use the sample time as low as possible, and though here we have chosen 1 microsecond. So we have an 80 ohm resistance, right? In between, we have a boost converter, and I've kept current ammeter and the voltage. This is input side capacitor, output side capacitor. So I'll show the values also. 10 microfarad, and then this measures the IPV, the current flowing out of the PV panel. And then this is your boost converter. We have an inductor, 5 millihenry, and then there is a switch which is connected to cater to the practical parameters into consideration. So I kept some very minimal finite resistance, right? And then there is a diode, and then the output capacitor and the load. So I've kept ammeters everywhere, and the whatever wherever capacitor is there, I've also kept the voltmeters, right? Now I'll discuss the MPPT algorithm. Hmm. So MPPT algorithm works in a way which is very simple to understand. The philosophy is very simple. What it does is it will measure the voltage and current coming from the PV panel. The current and voltage is fed to this MPPT algorithm. You can see here I and V. These are fed and they're multiplied. So you get at this sample what is the power produced from the PV panel, right? And then this power is compared with its own previous sample power. PPV is a power which is coming at this sample, and just previous sample, previous microsecond, whatever was the power was there, and that power is subtracted. So you get an error. This instant and the previous instant, what is a change in power? Similarly, the change in voltage is also noted, right? So based on the change in power and the change in voltage, that something you might have done, that's why the change has come, right? What change we might have done is the change in the duty ratio. When you change the duty ratio, as you recall the equations, so V naught is V naught output voltage will change as per the duty ratio. V naught is equal to VPV by 1 minus D. When you change the voltage once by one step, the power produced will also change. That's what we saw in the plant. If you can recall this, at every small change in the voltage, the power is also changing, right? Small change in the voltage, there is a change in power in the y-axis. So we are trying to see, actually our objective is to reach this point. It's a maximum power. But step by step we are rising. If you are in this part of the curve, first half of this curve, we're step by step, marching towards this maximum power. So how do we move step by step? We see the change in voltage, and if the change in voltage is bringing out a change in power which is positive, that means the present power is higher than the previous power, then we would recommend such a change for the next step also. On the other hand, let's say we are in this side of the curve, the change in voltage is here, the increase in the voltage is resulting in decrease in the power. And if we notice that increase in the voltage is ultimately resulting in decrease of the power, then we would suggest the opposite way. That means to decrease the voltage so that we reach this point. So at any given point of time, you have four possibilities, uh, bidirectional, in two halves, right? And ultimately you take a call either to increase the voltage or decrease the voltage, and increasing and decreasing the voltage is ultimately done by changing the duty ratio. So indirectly, what we are trying to do here is we change the duty ratio directly, and the change in the magnitude of duty ratio is a delta step that we are assumed to be 0.001, and we check the convention of the change in power and the change in voltage. This sign convention is used, wherein we get what is the change in power, and what is the magnitude of this sign convention of it, and depending upon the sign convention, either the duty is added or decreased, and ultimately we are step by step, inch by inch, moving towards that operating point which will get converged to the maximum operating point, right? So let me show you results by running it so that you have more clarity on whatever I've spoken. Okay, so if this boost converter is working properly, and if the MPPT algorithm is giving the right directions, then you should be able to track 2 kilowatt power, that is the maximum power from the photovoltaic panel to the load, right? So let's measure the power here. So I'm already measuring this is the output voltage across the load resistance and the output current. So if I open this, just a minute. Mm, what happened was this time. Mm, time. You can see here 2 kilowatt. You can see gradually we are reaching the point which is 2 kilowatt. This is the power being tracked. So if uh, if I change the load resistance, let's say I decrease the load resistance, let me say 20 ohms. Let's run this now and check. You can see the power is still 2 kilowatt. If I reduce further, let's say I'll keep it 10 ohms. If I keep it 10 ohms, you can see the power drastically reduces. It's no more 2 kilowatt. If I keep it 5 ohms, you could appreciate that it's far less, right? How much you're getting? This is around 600 watt. So why the power has reduced? Because we have already touched the limit. If you want to see what is the duty, this is a duty. So duty has already touched its limit, 0. That's what I was explaining here. If you touch this duty 0, where the resistance as seen from the PV panel is same as the load resistance, and that load resistance is putting the kind of a limit for the MPPT tracking. If the load resistance is towards the short circuit point, if it is very less, then you have very less margin to track the MPPT, and you will never be able to track the maximum power. So the power delivered will be less. That is the limitation of the boost converter that we could actually see through the simulation model also, right? So, and then further you can change the irradiations and check for different operating conditions, and you could really appreciate that the MPPT algorithm is really working well. So next, go to the another converter, which is buck converter. The same philosophy holds good. You know the operation of the buck converter, but the most important passive element required here is the input capacitor, because if this capacitor is not there, and let's say the switch is open for some time, then the power extracted from the PV panel will be zero, because there is no path for the flow of current. So henceforth, we are not able to extract maximum power from the PV panel. So we put this input capacitor to store the energy when the switch is open and discharge when the switch is closed. Thereby, from the PV panel perspective, we are not losing any energy, right? So this is the equations with the output voltage and the input voltage. V naught is equal to duty into VPV, and similarly, the current equation also can be linked. Then you get the resistance equations. RPV is equal to R naught by D square. Again, you put the limits. You get to know now that the two limits will be the open circuit point and the load line. Unlike the other case in the boost converter where the limits were the short circuit point and the load line, here it's open circuit point and the load line. And you can easily come to this conclusion that the load line resistance, if it is higher and if it is towards the open circuit point, then you have a limitation with respect to the buck converter to track the MPPT from the photovoltaic panel to the load. So on the other hand, if the load line meets this MPPT in anywhere above this MPPT point, then you will be able to track the MPPT. And the next converter is the buck boost converter, and then this is the circuit. And if you write down the equations and derive the points of the extreme operating points, so then you will be able to appreciate that both for d is equal to 1 and d is equal to 0, you get both the horizon, within this range you get the complete spectrum of freedom, wherein you can track the MPPT. So the whole philosophy is the perturbation method, which I've already discussed. Step by step, you reach the maximum power point tracking, right? And this is the algorithm where I was speaking about perturbations. If it is positive and change in power is positive, the next perturbation would be positive. Similarly, you have four possibilities, and then this algorithm is what we have implemented in the MATLAB also. And apart from this conventional P&O and incremental conductance techniques, some heuristics algorithms like PSO or AI-based genetic algorithms can be also adopted for a specific case if you have multiple peaks coming up because of shading occurring in the panel. So with the simple P&O method, you will never be able to track the global peak, but with this heuristic algorithms, you may be able to track the maximum power point for the entire panel, entire array. So that gives us a reasonably good understanding about the photovoltaic panel. Now let's move on to the wind energy. So wind energy is also another important prominent energy resources that is seen and widely implemented across the world. Denmark, China, US, Australia, India, various countries across the globe, significant investment and research being carried out in the wind energy sector. So huge potential also, you can see with the numbers. It is estimated that even if 1% of the wind energy is used effectively, it can satisfy the global power demand. There are two types of wind power plants, offshore and onshore. So offshore plant means a plant which is far away from the shore. That means in the within the water, saline water. Onshore means it is on the land basically. So both offshore and onshore wind power plants are gaining a lot of popularity. So types of wind turbines, horizontal axis and the vertical axis. Mostly we go for horizontal axis wind turbines, where the axis of hub rotation is parallel to the ground, and vertical axis where the axis of rotation is perpendicular to the ground. So these are the components of the wind power plant. I've also numbered it. You can see there is a foundation, a huge civil foundation is required, because it has to hold the entire structure. And then this is a cable which is running from all the way from the generator, the yellow color one, and here you have a transformer, or you may get connected to the main grid. And this is a tower. The height of the tower is decided based on the wind speed, and depending upon this on the location also, and economics as well. So to rise the height of the plant so that you can capture the high wind which is available at the heights. And then access ladder, which is required for the maintenance and installation purposes. And then fifth one is a wind oriented control. So this structure can be rotated so that we can reorient our wind blades. If the wind direction changes, we need to reorient our wind blades so that we can capture that wind power. And then you have a nacelle. Sixth one is a nacelle, this one where we house the wind blades, the hub, the generators, and all of them. And then the seventh one is a gearbox, this red color one. This is a this is a generator, so which is coupled with the turbine, so that as turbine rotates, so the generator will generate the electricity which is taken out from this cable and get and is being fed to the grid. And then your anemometer is there, which will help us to give the direction of the wind velocity and the speed also. And ninth one is a mechanical brake to prevent motion of the turbine for the maintenance purpose. And then there is a gearbox. You might have observed this practically also. The practical wind turbine, while you are traveling by train, you might have observed this at the hilly stations. It is rotating very slowly, but internally there is a gearbox which will convert the high torque, low speed turbine to the high speed and low torque generator, because ultimately we need to generate electricity which is compatible with the grid frequency. So you need reasonably good amount of speed to generate the power at 50 hertz in the Indian grid scenarios. So there is a gearbox which is a mechanical converter, and then there is rotor blades to access the wind energy. And the blade pitch angle control is a very important control mechanism which will help us to obtain maximum power, also to help us curtail the power in case of the high wind velocities, which is quite dangerous for the wind plant to sustain. And the rotor hub, which is the actual body which will convert kinetic energy from wind to the drivetrain. So these are the main integral components of any typical high-rise wind structure that you might have come across. And then this is a schematic of the wind energy conversion system. What you really have is kinetic energy coming from the wind applied to the wind turbines. By the aerodynamic principles, blade starts rotating and getting connected to the gearbox, which is a mechanical converter, converts from high torque to the low torque, or low speed to the high speed. And then it's coupled to the generator. You have some power converters for the power conditionings, and the transformer to meet out the requirement of the AC grid, right? So typical wind turbine with steady wind power. If you want to plot these characteristics, you see, as you might have seen this graph. So as wind velocity increases, the power output will change non-linearly, and that is given by this expression: Pm is equal to Cp, which is a function of lambda, which is tip speed ratio, and the blade pitch angle beta. Rho is the air density, area A is the area of the blade, V wind is the wind velocity. And the interesting thing is most of the things are constant. So the power produced significantly changes even with the drastic, even if a small amount of wind velocity, if it is changed. The reason being the relationship is not linear, it's non-linear, right? So there are three different operating speeds, which is quite important for us to recognize, as we have operating points defined in the photovoltaic panel, that is short circuit point, MPPT point, and the open circuit point. Here we have a cutting speed. After this cutting speed, you actually get some amount of power that you can offer it to the grid, right? So cutting speed is where you actually start generating the electricity, and then you reach the rated speed at which you generate the rated power, and then the cutout speed, which is quite harmful speed for generator to generate at this operating point. and we would like to disconnect our wind plant from at this point, from this point onwards. And if you want to plot, just zoom in this portion of the curve, just take it out and then zoom in, and want to study across different wind velocities, you get to know that turbine power output as plotted against the rotor speed for varying wind speeds. You can see that the power produced will change as the wind velocity changes. And remember that the blade pitch angle is kept 0 degree here. And if I increase the blade pitch angle to 1 degree for the same wind velocities and for the same turbine of your interest, you can see that the power output will decrease at, let's say, the 14.4 meter per second. The reason being, the blade pitch angle, if it increases, so it will change the direction of the wind velocity as applied to this, as seen from the wind blade. So angle of attack can be changed. If angle of attack is changed, the force applied to the wind blades, that gets reduced, and then the power output from the entire turbine or the wind plant will reduce. So typically we have these three means of speed controls: the pitch angle control, the yaw control, and the rotor speed control. The pitch angle control, where the closed loop control mechanism, you change the wind blade orientation as seen from the wind velocities. So, and then there is a yaw control where you actually rotate the entire vertical structure and then reorient your direction so that you capture the change in wind velocities, wind directions basically. And the rotor speed control, as plotted here. So at a particular rotor speed, you get a maximum power. So this rotor speed control is very much essential to track the MPPT during a fixed wind velocity. So the types of generators, wind generators that are available in the commercial side. So we have squirrel cage induction generator, where we go for squirrel cage induction machine. You must be knowing the philosophy of operation of a squirrel cage induction machine. The rotor is short circuited, and you don't have accessibility to the outside world. So the torque and the speed is more or less the constant, and henceforth this kind of generators are not very friendly if you are interested to extract maximum power, because you will not be able to change the rotor speed. That is not in your hand. So whatever is the wind velocity and whatever power that is generating, more or less you have to be happy with that. And then there is a wound rod induction machine where the speed variation is 10%, and then you have a variable resistor. When you have a variable resistor, so the torque changes, but there will be power loss, and henceforth it's not so economical also. So then the most important type of generator, what we call it as a type 3 generator, very widely adopted even in this country. Suzlon, the one of the top manufacturers, and they have a lot. They have the plants across the country, and if you go to their website and see, 2.1 megawatt standard W-fed induction machine is what they have installed at various places. So what is this specialty about this W-fed induction machine? You see there is a wind blades connected to this gearbox, and it's coupled to the W-fed induction machine stator. It's a slip ring induction machine. You have a stator which is directly connected to the grid, and you have a rotor which is connected to the grid or the point of common coupling with the help of back-to-back converters. The converters, there are two converters. One converter is looking at the machine side, which we call it as a machine side converter or the rotor side converter, and there is another converter which is adjacent to this converter, which we call it as a grid side converter. So I'll explain in detail about that. So, and then the another type of topology in terms of generator selection that is available is the fully variable type, that is where you go for permanent magnet synchronous generators, and you have a rated converters being placed here. So here the 100% speed variation is feasible, but for economical reasons and for for various other reasons, like the reactive power compensation capability and controllability and reliability and various moderate reasons. So we go for double fed induction machine. So I'll I would like to take some time to explain this. So if you see here, the slip ring induction machine, the stator is connected to the grid, rotor is connected via the back-to-back converters. So let's say the wind velocity has changed and you're operating at a speed which is less than the synchronous speed. Let's say the synchronous speed of this machine is 1000 rpm, and at 1000 rpm I'll be able to generate 50 hertz that can be directly synchronized with the grid. And wind velocity is not in our control due to any reason. If wind velocity is down, and because of which the rotor speed is also down, then the speed will be less than 1000 rpm. And a speed less than 1000 rpm, I cannot directly connect my system to the grid, because for the fundamental requirement for grid synchronization is the frequency should match. So how does this this type of generator would function then? What actually happens is, in real time, because these converters are very fast acting switches, so this particular converter, which is a grid side converter, right? So the grid side converter would borrow some power from the point of common coupling or the utility for that matter, and is fed to this DC link capacitor. Now this DC link capacitor, and how much power that it would pump, it depends upon the DC link voltage. And the DC link voltage will be dropped because a power is pulled out from this DC side to the AC side, because you need some amount of power which is lagging from the wind system perspective, and that lacking power is pulled out from the DC side with the help of this rotor side converter and is pumped to the point of common coupling, wherein the power flowing from the rotor side and the power directly coming from the wind plant, both of them combined together looks like a 50 hertz system being connected to the utility grid, right? So the rotor side converter would initially function, it will pull some power, and there is a dip in the voltage at the DC link capacitor, and based on the reference value and the dip in the voltage, the grid side converter would pull out the power which is appropriately required to maintain the DC link voltage constant there, right? So on the other hand, let's say that if there is an excess of wind velocity, that means now the speed, synchronous speed, it has crossed, and let's say 51 hertz or 52 hertz is the power that you're generating at this frequency. Then this is also not ideal for the grid, because you need 50 hertz anyway. So that means now the rotor side converter would think that there is something which is in addition to what is actually needed to directly get connected to the grid, and let me pull out that aspect of power, and this rotor side converter will take out that additional component of power which was in excess available, and then push it to the DC link capacitor. Now the DC link voltage, just recall whatever the statements that we have made during the initial part of the presentation. If the power is in excess in the DC side, active power, then there is a shoot up in the voltage. If power is less, then there is a drop in the voltage. Now there is a shoot up in the voltage during the super synchronous mode of operation, and the reference value remains the same. Now the grid side converter would think that I need to do something so that I can bring down the voltage. What you need to do? Then you need to inject power to the grid so that this voltage will drop down, and the same thing will happen, and the control action would work excellently, so that in real time, irrespective of the wind velocity variations, and this particular converter combination work together hand in hand to help the system to push the power into the grid, right? So whatever I've explained, it's been little more detail in this converter, in this control strategy that is being displayed here. So you actually sense the currents in both the rotor side converter and the grid side converter. You sense the voltages, right? And then there will be transformations. I hope you all are familiar about the inverter controls. We go for ABC to DQ transformations, because the PI controller will be very happy to function if there is a DC signal which is being compared and then that is given to it. So to convert AC signals to the DC signals, you go for the transformations, and then ABC to DQ transformation, and then you decouple them. Then you have a D control and the Q control, and the D control will help us to take care of the active power, and the Q control will take care of the reactive power. So that, and there is also a outer voltage bus control loop, so that the dual control loop will function hand in hand to maintain the DC link voltage constant, and then supporting roadside converter to support the machine during the subsynchronous and the super synchronous mode of operations. In the rotor side converter, again there is a D axis and the Q axis control. Here the Q axis control will help us to track the MPPT. Now I'll discuss how we'll track the MPPT in this W-fed induction machine. So in the machine language, probably you might have learned this, that the torque and the speed is nothing but the power. The product of torque and the speed is the power. And the torque, how do you express the torque? The torque is expressed in terms of the flux and the current, right? So what we actually do is, the flux remains the constant. The stator flux remains the constant because it is connected to the infinite grid. Flux is a parameter which is dependent on the grid voltage. So flux remains the constant. And then if you change the current, then the torque changes. If the torque changes, then the speed changes. If the torque and speed changes, then the power changes, right? So what we actually do is, if you see this rotor, please understand, if I change the current output from this machine, if I increase the current output from this machine, the speed will decrease, because it's like loading will increase on the system, so the speed will decrease. Exactly the same philosophy of the synchronous machine, right? So what we actually do is, and you actually might have noticed this properly, if I change the speed, at a particular speed there's a maximum power. So what we actually do is, step by step, inch by inch, we change the current, or a small portion of current is changed, and we observe what is the change in the power output. And then eventually we get to know, for this particular rotor speed, at this wind velocity, we are getting maximum power. And then you tabulate it. And then once you choose the wind velocity, it will automatically give you, this is the speed that you need to suppose to act, so that you track the maximum power. And in addition to this rotor speed control, you also have a pitch angle control mechanism, as I already declared. So this will be helpful to track the maximum power, and especially it is used for high wind velocity conditions, and rotor speed control is used for low wind speed conditions. So some of the research areas of the W-fed induction generator. So one of the biggest challenge the W-fed induction generator, in spite of its numerous advantages, which is well studied and researched, and many research ideas have come out of this research problem, and that challenge is low voltage right through. What really happens is, due to some reasons, and this, let's say this W-fed induction machine is connected to the infinite grid, and if there is a fault somewhere in the system, and the fault in the system is reflected as dip in the voltage, right? So if there is a dip in the voltage, I just now declared that the fundamental electricity, the principle is, the flux is a state variable, and the flux cannot change by itself suddenly, but flux is a dependent variable on the voltage. But the voltage has changed drastically, and flux will oppose the sudden change of the voltage in its own language by introducing a DC component of a flux. That means a DC transient is introduced. And before this fault, what was happening was, it's an AC system, current and voltage is sinusoidal, the flux is sinusoidal, and the rotor speed, the slip is, let's say, 0.1, and is closely operating at synchronous speed. And then what happens is, the relative difference between the flux and the rotor speed is very narrow. The rotor speed is, because it's a three-phase system and they're distributed, and you may recall it, there is a rotating magnetic field rotating at a speed of synchronous speed. So there is a rotating speed of magnetic field being cut by the rotor, which is rotating close to rotating speed, so the relative difference of speed variation is very less. So the magnitude of induced EMF on the rotor circuit is very less. And henceforth, these converters are rated for only 30%. Because this, I mean, you may recall the basic induction machine principles. The power in the rotor side is slip times of the stator power. The slip variation is in the range of 30, plus or minus 30%. So the power converters are rated only 30%, unlike the type 4 converter, type 4 generators, where you have a full rated converters connected to the stator side. So the real-time operation is fantastic, absolutely no problem. But if there is a change in voltage, or there is a dip in the voltage, the DC transient of the flux, which is caused at the stator side as an opposition to this change in the voltage, and that DC transient flux is seen as a constant as seen from the rotor side. But the rotor, being a mechanical device, cannot change its speed drastically instantaneously. Electrical parameters can change, but mechanical parameters has its own inertia. It's an interlocking system between mechanical and electrical system. So whenever something sudden happens on the electrical side, so mechanical side will suffer, right? You know all this rotor angle stability and all of those things. So what will happen now is immediately there is a reflection, or the impact as is seen on the rotor side. That impact is seen in terms of increased voltage, because there is a relative speed variation is quite large, a DC cut by a high rotating mass, and the EMF gets induced according to the Faraday's law of electromagnetic induction. And then the EMF gets induced, dynamically induced EMF, by flux cutting principle, and this voltage is rated way above the rated capacity of these converters, and the switches may have to carry the large amount of current which they are not supposed to carry, and this extra power being pulled out by the switches is now reflected across the DC link capacitor, and this DC link capacitor is a vulnerable device which may blow off. And also the this grid is not receptive of receiving any active power at this point of time. So because the power output from the stator will also reduce, the rotor speed will also increase. So what are the sequence of events? The voltage dips, flux, there is a DC transient of flux, rotor speed cannot change, and because of which there is a huge amount of voltage induced on the rotor side, and the current will flow, increased value of current will flow, the the insulation material of the converters may blow off, or the converters current carrying capability is also limited, that may also blow off. And the most vulnerable point, which is a DC link capacitor, that may also get damaged. And because the grid is not receptive, the the rotor speed will also increase beyond its limit, which is quite dangerous from the mechanical safety perspective. So overall, the essence is the doubly-fed induction machine will suffer because of getting interconnected to a faulty system. But what's the grid code suggest, my dear friends? The grid codes, the LVRT grid codes suggest different grid codes given by different countries. I know you have a German grid code. German grid code is quite deadly. You see here, for a quite a big capacity um, of wind plants, let's say if it is 5 megawatt, 10 megawatt, if you have a series of wind turbines connected. So what this suggests is you're supposed to get connected to the system even if it is zero voltage right through. That means even if it is a bolted short circuit fault at the grid side for some duration. See the amount of struggle that DFIG has to pass through during this time, right? So, and then there is Spain grid code, British grid codes, Danish, Italian, Indian. India also has its own grid codes. Depending upon the severity of the grid code demands, and they will not be able to disconnect in these regions. The regions, the boundaries that is being laid out here within this region, they will not be able to basically get disconnected from the grid. Not only getting disconnected, they're also supposed to support the grid by injecting the reactive power. This is another challenge, right? So many such solution methodologies have been placed in the literature, worked out in the literature. One such conventional approach, and it broadly can be categorized into hardware approach and a software approach. In the hardware approach, you have a crowbar protection, wherein the rotor circuit, basically what they do is, at the rotor side, they will connect the resistors. So the solution, the idea behind this solution technique is, if there is a dip in the voltage, and because there is a excess of energy available in the rotor side, and that gets discharged at the rotor circuit through these resistors, so that your converter switches and the capacitors, they get protected. The idea looks to be very simple and quite promising, but there is a hidden challenge here. The reason being, because once you start once you short circuit your rotor side, then this machine will behave like an induction motor. Induction motor, we all know, it will draw reactive power from the grid, right? So, but during the time of fault, where the grid itself is struggling hard to maintain the voltage profile which is connected to the reactive power capacity of the grid or reserve available at the grid, and if there is a guy who is expected to support the grid by injecting the reactive power according to IEEE 1547 standards, rather this person is drawing the power from the grid to protect himself. So in that regard, this is a serious offense from the grid perspective, and it will deteriorate the operating condition of the grid, right? So henceforth, crowbar protection is not finding a great acceptance rate in the real field. And the other solution techniques include the DC to DC chopper, where a switch with a resistor connected the DC link capacitor to protect the DC link capacitor. So this may work fine to protect the DC link capacitor, but it has its own challenges and limitations, because it is not going to support the switches for its protection. So, and then the dynamic voltage restorer, DVR, is also another interesting solution in terms of hardware approach. So wherein what they actually do is, they connect a series transformer, and then to the other side of the series transformer they connect a inverter. So the idea is very simple. If the root cause of all the problem is the dip in the voltage, so this transformer and this DVR arrangement, basically the inverter control, would sense the amount of dip in the voltage, and at least at this point of common coupling, which is closely connected to the W-fed induction generator, it will try to compensate by injecting the voltage, and that much voltage which is dropped because of the fault, so that you're trying to solve the problem at the root end itself. But there's additional investment, and going for full rated DVR is quite expensive, and in real time, and it may also consume some power during the steady state operation, which is not so efficient actually. And similarly, there is a concept of a D-STATCOM, distribution STATCOM, which is capable of injecting and absorbing the reactive power. Bidirectional power support is possible. During the steady state operation also, they can be supportive in terms of maintaining the power factor, and during the transient and dynamics conditions, especially during the fault, could be balanced or unbalanced fault. D-STATCOM can be configured to take care of the requirement of the grid codes. But unfortunately, this will also add to the overall investment of the W-fed induction machine. So, and then the another important solution methodology that is quite researched in the area of low voltage right through capacity enhancement of a W-fed induction machine is that of the implementation of a fault current limiter. So the fault current limiter is placed. Fault current limiter inherently is an impedance or a resistance which is offered to the system at some point of time. That means electrically, this resistance or impedance is seen whenever there is a fault, and that is connected in between double fed induction machine and the grid. And if there is no fault, then this fault current limiter, is physically there but electrically gets disconnected, so that you may look like a small resistance being connected in series, so which is not so significant. So they indirectly not so much consuming electricity from the grid during the normal operation, but are of great help during the fault grid conditions. What they actually do is they limit the value of fault current being produced from the double fed induction generator, or they indirectly support the system point of common coupling, the voltage collapse at the point of common coupling. Thereby, the impact on the grid, impact on the double fed induction generator can be reduced. And apart from the hardware techniques that we have discussed, we also have software techniques. The software solution, in nutshell, if I have to say, it's quite simple, wherein the idea behind this software approach is trying to counter attack the magnetizing component of the flux, which is responsible for the increased voltage that is seen at the rotor circuit. So you already have a converters, use these back-to-back converters, and then you have a DC link capacitor also. You just counteract, you just inject the opposite magnitude of current, or demagnetizing current is being pushed into the grid via this converter, so that the impact of this magnetizing component of current on the grid can be avoided, on the converters can be avoided. So the other research areas include the inertia control, the power quality. You must be very aware of, very much aware of what is happening in the grid, because a lot of power electronics converters are being placed. We are going to lose the system inertia, which is very much responsible for maintaining the frequency, the primary frequency control. So grid inertia need to be maintained. Fortunately, with this double fed induction machine, you already have a rotating mass, unlike the solar photovoltaics, so that can be used to support the inertia. And the power quality, like the grid side converters and the rotor side converters, they can be embedded with this active filter capabilities, so that if there is a nonlinear load connected at the point of common coupling, so the harmonics can be mitigated and the reactive power compensation can also be done. And then the voltage control of the network, for example, if you have a double fed induction machine which is acting or working together with other voltage compensating devices like on load type changing transformer, D-statcoms, and the capacitor switching banks, and how do you manage all of them to optimize the system components, and thereby improving the voltage profile of the network, right? And the cost effective hybrid system architecture, which is also very important topic, because today only we had a discussion with GE, General Electric. They are in collaboration with us. So they were talking to us, requesting for collaboration in the area of wind solar hybrid system architecture, so which is very important, as on uh, they'll be able to in a way uh, optimize the system architectures. I'll discuss, if time permits. It is one of my research topics during my PhD, where we combine the double fed induction generator with the DC microgrid, and then we come up with a cost-effective architecture where, during the grid-connected mode of operation, the grid side converter of the double fed induction machine was used by this solar photovoltaic-based DC microgrid to exchange power with the grid, so that the additional inverter which otherwise would have required is to exchange the power can be eliminated. And then during the isolated operation, the same grid side converter can be configured to push power from the wind power plant to the DC microgrid, so that we can improve the reliability. And also the fault rate through can also be effectively done, because DC microgrid has a super capacitor which will be helpful to reduce burden upon the DC link capacitor, so that we can protect the DC link capacitor as well. So cost effective hybrid system architecture is also becoming very popular, and industry is also showing a lot of interest in this direction. And the loss minimization of the network, we all know what is loss. System losses can be to certain extent can be minimized by adjusting the reactive power flow. And because we have a back-to-back converters with the double fed induction machine, so the reactive power compensation can be well achieved. And the isolated power feeding to the DC grid is one of the famous topologies, which is well researched in the In the European side, especially two authors, they have come up with some 40, 50 IEEE journals, if I'm not wrong. So it's a dedicated topology where double-fed induction machine is pumping power to the isolated DC grid and addressing the wake effect. The numerous research topics, we can go on and go on and go on. Sensorless speed control, HVDC power transmission, especially for offshore wind farms. And wake effect is an effect which is seen when you have large number of wind turbines connected in different rows, because the first rows of wind turbines would get raw wind speed, right? But as the wind blades rotate, they create disturbance or turbulence, and the wind velocity that is received by the second row of wind turbines in a wind farm gets a disturbed wind velocity, basically, because of which the overall wind power output, the plant power output, will decrease. That's what we call it as wake effect. And you need to have an optimal distance between two rows of wind turbines, and it should be around 10 times the what is that, the size of the wind blade. So that much bare minimum distance should be kept, and optimal sizing of the location. There is a model called as Jenkinson model. So he has done research on this. So uh, to take care of the wake effect also. So, and this was, I was discussing about wind farms. You can see here wake effect. So first row of wind turbines, they don't experience any turbulence, but subsequently you can see a lot of turbulence, and overall power output will decrease. Right. So we have covered in detail about wind, solar, photovoltaics, MPPT, boost converter, demo, MATLAB, and all of them. So the different converters already discussed. I don't want to discuss again and again. So, but I just wanted to mention about the usage of bidirectional converters, which are connected to this battery and the ultra capacitors. So, unlike the unidirectional converter, which is connected to the photovoltaics, these bidirectional converters, which are connected to this battery and ultra capacitors, are very much helpful, because during the isolated operation of the DC microgrid, so at times there could be an excess of energy seen at the DC bus, because the load could be less, or solar photovoltaics could be high. The generation from solar photovoltaic panel could be high. In that case, you need to discharge energy, because you need to maintain the voltage stability anyway. So what this bidirectional converter would do is, it will help the battery to get charged from this DC bus, right? And on the other hand, if there is a lack of energy on the DC bus, the whatever is the stored energy from the battery is pushed to the DC bus. So what is the role of the ultra capacitor? Ultra capacitor is a high power density device, unlike the battery, which is a high energy density device. So this ultra capacitor would absorb the transients, that switchings that is coming up because of changing the irradiation, power output being reflected as a sudden change on the DC bus, or if there is sudden switching of the loads due to any dynamics that you see on the DC bus. The reflection of these dynamics should not be directly applied to the battery, otherwise the life of the battery will also go down. So what we usually do is, we connect the ultra capacitor across this battery, so that this ultra capacitor would absorb these transients, and hence the battery life can also be improved. So bidirectional converters connected across this battery and supercapacitor is eventually helpful to maintain the DC bus voltage constant, and thereby the energy transition from the generation to the load is happening quite smoothly, right? So classic converters I've already listed, the bidirectional converters also. So the different topologies, I'm not going to go in detail. So this is the whole philosophy. There is a reference current and the actual current. You have a PA controller and the limits, and ultimately the desired output is achieved. So you have a DC to AC inverters, three phase, single phase, half bridge, full bridge, two level, three level, multiple topologies with silicon, with wide band gap converters, with different PWM techniques, sine PWMs, SVPWM. Hundreds of varieties of combinations are possible depending upon the operating conditions and the economics and the requirement. You choose any one of them, right? So these are the basic control strategies of the inverters, and I've already discussed with respect to the DFIG. More or less, it looks the same. Hysteresis current control is also one of the widely researched controller, because unlike the PI controller which is operating on a DC platform, so you don't have to convert from ABC to DQ. You can directly use this hysteresis current controller, and then the AC signal can be compared directly, and then the switching pulses can be generated. But the only challenge with this hysteresis controller is the filter size. Choosing the proper filter size would be challenging because of this variable because of the fixed bandwidth. Or the other option could be go for a variable bandwidth, and the switching frequency can be fixed. And if the switching frequency can be fixed, then that is helpful for us to choose the filter size. So these are 2 level and 3 level inverters. This is current controller. I don't want to go in detail now. Right. So the types of DC microgrid controller: decentralized controller, distributed control, and centralized controller. And the decentralized controller, there is no communication channels that is connected basically. Everything is operated by local physics, sensors, and control action. In centralized control, there is a different microgrids, and they talk to a centralized controller, and there is a communication channel dedicated, which will get to know, which will in real time sense what is really happening in the microgrid and give the command, which is globally impactful. Right. And the distributed control, the challenge with the decentralized control scheme is you really don't know what is really happening in the other side of the network, because you're just worried about you're controlling your own local parameters. In the centralized controller, you're always busy taking care of the entire global system. So the global system, the advantage is you get to know in detail about the everything that is happening in the system. But the challenge could be there could be communication delays, attacks, and cyber threats, man in the middle attack, all these things, right? False data injections. So because of which there could be lack of security and stability in the system, right? In the distributed control, you inherit the advantage of the decentralized and the distributed control, and the centralized control also. So decentralized control, typically we go for droop control mechanism, voltage leveling, DC bus signaling, power line signaling methods. So in the conventional droop control, you must be knowing this, right? So if the slope is 0, then you share the maximum power. If the slope is infinity, you don't share any power. So if there are two different units with different slopes based on the ratings, and they share power accordingly, so that you actually don't overburden any one of the converters. But conventional group control, if you have a good voltage regulation, and the challenge will be that the power sharing will be bad. Or if you have a good power sharing, then the voltage regulation will be bad. So then there are different other techniques like virtual resistance based group control, adaptive group control, and then intelligent technique based group control, adaptive group control. Various things are there. Then grid connected mode of operation, the objective would be to extract maximum power from the DC microgrid system and then feed it to the grid, right? So PV is operating in MPPT, and then battery could be charging or discharging or kept idle also. Loads are connected, and the inverter which is connecting the DC microgrid with the grid will be responsible for maintaining the DC link voltage constant, and it is bidirectional in nature, right? In the isolated system, there is no inverter role, and then the DC link voltage or DC bus voltage is maintained with the help of battery and petrol capacitor. PV again is operating in MPPT, and there are multi-islanded DC microgrids operation and control, because if there are multiple microgrids, and one microgrid can act like a virtual power plant, acting like a master node, and other can talk to them, and they sharing the power among themselves. So some case studies are also there. Permanent magnet synchronous generator, loads. These are in detail about how this is quite important. BEMS, battery energy management system. You must be knowing, each battery packs will have its own BMS, which in real time administers the operating temperature, current, limits of individual battery cell. And if there is any battery cell which is going wrong, it will try to disconnect, and ensure that the cooling system is working properly, because battery is a very cumbersome technology. It's not just straightforward. Each cell voltage balancing, current balancing, power balancing, thermal constraints, all of them should be taken into consideration. Otherwise, the battery life would go down, right? And unfortunately, I would like to say that most of the products that we get from the neighbor countries, the BMS also we receive from the neighbor countries, right? So the BMS, we never know, all of these battery packs that we are using, the data can be also stored somewhere else. So it's a kind of lack of security. So the researchers who are there in this call, if they're interested to design their own BMS, that is very really helpful for the country actually. So photovoltaic system I've already discussed in detail. Let's not repeat the stuff. And then islanded operation of single microgrid, and depending upon the state of charge of the battery, you either charge, discharge. Please note down that the battery has its limits between 10 percentage and to 90 percentage. You can operate the battery storage system, and you're not supposed to go for deep discharge or supercharge the battery, because both of them will degrade the life cycle of the battery. And different energy storage technologies for renewables like mechanical, electrochemical, thermal, electricity, hydrogen, gravity storage. So numerous applications. Maybe I'll stop here because to explain the real-time case studies, maybe I'll require another half an hour. So we'll discuss in some other FTP. Right now, I'll stop here, and if there is any questions that you want to ask me, let's open the floor for the question and answers. Thank you so much. Over to the organizers. Yeah.
Thank you, sir. That was very knowledgeable. So there are some questions. Naren sir is asking that do we have wind power generation over high-rise buildings in anywhere in India?
As per my knowledge, we may not have. Maybe in Tamil Nadu we may have. I don't know. I don't think so, because in high-rise apartments, putting a wind turbine, how secure is this? I don't know, because there could be some, movement of planes and this and that. I really don't know. Maybe it's not there.
And sir, another question. Do we have a wind power included in the wind power green power market for PPAs?
PPS, green power market, I don't think it is there. PPS are there. You can go for day ahead green D, green power. You can bid the power basically. Dam, G dam, this is there, right? Day ahead market. So PPA may not be there as of now.
Sir, one question from my side.
Yeah.
Actually, you told about the, but initially you told the formula about RPV is equal to R naught upon 1 minus D square. And for boost converter.
Yeah.
Then afterwards, when you were decreasing the R naught, power was decreasing in the simulation part.
Correct.
Then can we justify this thing like if we are decreasing R naught, then RPV will also be decreasing? And it means that the PV is getting short circuited.
Correct. That's what is happening.
So that's
what is really happening. If you're reducing or not, then RPV is decreasing, and then you're moving towards the short circuit point.
That's why the power is decreasing.
Correct. The current will increase. Current will increase, but the power will decrease because voltage will decrease.
Okay. Yes, sir. Yeah. Sir, another one question from Ashim Bandal, sir. What tools can be used to model a hybrid microgrid for power supply or EV charging applications? Additionally, how can we calculate the cost efficiency of such a system?
What tools here? He's asking about software tools?
I think so, yes, sir.
If you want to go for software tools for EV charging application, maybe hybrid, solar, wind, such kind of topologies. Real-time platform, anything could be fine. We have RSCAD here, which is quite good actually. Or if you have Opalati and all of them, any of these real-time toolbox you can take up, try to model them. Yeah, which is, accuracy level of model will be very high actually there.
Thank you, sir.
Yeah.
Are there any more questions? There are no more questions. So shall we close the session?
Yes. Thank you so much. I wish you all the best. Yeah.
Thank you.